So in this next video, we talk about when a limit would not exist. And so in the previous video, we kind of talked about we're looking for a pattern as we get close to a certain x value. Are we sensing that the y values from either side are kind of getting close to the same level? So in this case, we need to be looking for some reasons why it may not exist. The first reason, it's actually not listed here, but if the x value that we're looking at is not part of the function's domain, there's not going to be a limit. So if you were to look at the square root of x, that function, and we're trying to find a limit when x equals -10, well, the function doesn't exist there, so we're not going to have anything to worry about. So we're more thinking in this video what happens when the x value is somehow part of the domain of the function. So that's one thing that you might want to jot down there, is that you have to make sure it's part of the domain of the function for it to actually exist. So if we look at example 1, the limit as x approaches 0 of the absolute value of x divided by x, and we just think about graphically what that's going to do. On the right side, when all the x values are positive anyways, absolute value doesn't really do anything. So I'm going to really be taking a number and dividing it by the same number, and that's just going to get me 1. So over on this side, I'm just going to be at a height of 1 the entire time. But on the left side, when those x values are negative, now that seems to matter a little bit more, because I'm going to take a negative number and make it positive, but then divide by the negative version of that number, and that will always get me -1. So it doesn't matter if I'm looking at x equals -5 or -7 or -10. It's always going to be, in the end, the positive version of that number divided by the negative version of that number, and that's going to simplify to -1. Okay, so this is a case where the limit would not exist, because as I get close to x equals 0, we're approaching different levels from both the right side and the left side. So they have to match up. We have to see the same pattern from both left and right sides if there's going to be a limit. Okay, in example B, we're looking at 1 over x minus 1 squared. So we've kind of looked at 1 over x squared before. That's that volcano shape. This has just been shifted 1 to the right. So we kind of know what it looks like already. It's going to have that vertical asymptote right there. And then it would have this sort of thing going on there. And that sort of thing going on there. So as we get close to x equals 1, because that's what we're focused on right here, from the right side it's getting really big, and from the left side it's getting really big. They're both approaching infinity. So in some ways you might make an argument that there would be a limit here. But it has to equal an actual number from the left and right side. And the idea of infinity, it's an idea, it's a concept. So this is one where most textbooks would say there is no limit, because the number idea that we're getting close to is infinity. There are a handful of textbooks that would read that differently, and I understand if you would want to say there's a limit there, but in the end we would have to say there's no limit for this one. So when the pattern is infinity or negative infinity, we generally say no limit. Okay, then our last one is really not one that we're going to look at a whole lot, but I think it's kind of interesting just to see what would happen if we looked at a graph of sine of 1 over x. So you can certainly do this, especially looking around x equals 0. I'm not going to take the time to show you a graph right now, but what I want you to notice is the x values as we're moving down this chart here. It's 2 over pi, 2 over 3 pi, 2 over 5 pi. The denominator keeps getting bigger and the numerator stays the same. So as we're going down this way, we are getting closer to x equaling 0. So in our overall function, sine of 1 over x, the denominator keeps getting closer and closer to 0. We need to think about what's happening. So if I were to actually kind of graph this or think about making a chart, you're going to notice a pattern for these values. You just get 1, and then -1, and then 1, and then -1, and then 1, and then -1, and then 1. There's no pattern here. It just goes back and forth, back and forth, back and forth. So we call this oscillation, and if you think about how these things would be spaced out, these x values are actually getting closer and closer and closer together. So it's a squiggly line, but the squiggles keep getting closer and closer together too. So in a situation like this, we would not have a limit, but it's something that we would rarely look at. So that's all I want to cover in this next video, just some examples of where we would not see a limit. And you can kind of see pictures right now. We talked about this oscillation in part C, In part A, we talked about if the left and right sides just don't match up. And in part B, infinity is a bad thing as well. And then overall, you should also jot down, it has to be part of the domain. The x value that we're looking at has to be part of the domain for this to work too.